Okay, I've tried to brainstorm a few ways to try to explain polarity and then the sigma and pi bonds. I didn't really come up with a very good way, but I'm going to try this again, and hopefully some of you may like this a little bit better. So the toothpicks are back, and this time I have fruit snacks instead of marshmallows. So my central atom is going to be the grapes, and I'm going to make a tetrahedral molecule here. Okay. 3. All right, now. So this is my central molecule, and now I'm going to make all of my other atoms on here strawberries. All right. Now, let's see here. Because I know some of you are having a really hard time with, what does it mean when she says it has a top? Okay, so if you look at this, this is a non-polar molecule, because if I turn it any which way, all of the bond angles are the same, and you can't tell which atom is which. This is in the middle, but you can't tell any of the ends. So for example, if this is hydrogen, if the strawberries represent hydrogen, the carbon-hydrogen bond, when you look at it on the electronegativity chart, the electronegativity chart will say, oh, this is a nonpolar bond. Okay, well, a nonpolar bond, you have 4 nonpolar bonds, it's a nonpolar molecule. That makes things easy. However, it gets more complicated when you have polar bonds in a molecule. So let's say, for example, that the strawberries are now chlorine. Well, carbon-chlorine bond is polar. However, if I tell you, now I'm not a magician, but if I tell you, I want you to remember where this chlorine is, and then I'm going to take it away, and I'm going to smush it around a few times. Can you tell me which chlorine I was talking about? No, you can't. And that's the point. So even though these bonds are polar, the molecule itself is not polar, because all these angles are the same, and so in 3D they cancel each other out. Now, if we were to take something like lone pairs, so here, let me take this off. So here we have a trigonal pyramidal molecule now. All right, this is a polar molecule, because if I tell you to look for this one, I can turn it and you go, oh, yeah, I can find it. You can find them. You can get oriented to the molecule easily. So when I refer to a top, like this would be a lone pair, like I call this the top of the molecule. Even if it's like this, you can go, oh, yeah, you can definitely differentiate that this molecule has a top and a bottom, a left and a right. That's what a polar molecule means. And so generally, if you have lone pairs are really easy to find out in space. So like water here. Water, this is, well, first of all, here, this would be oxygen, and these two are hydrogens. So these bonds here, they're polar. So they're polar bonds, and look, it doesn't matter which way I turn it. You can go, oh yeah, I can find the top or the bottom of that molecule. That's what makes it polar. Now let me go back to my wonderful tetrahedral molecule here. Now, other things that can make something polar. What, instead of lone pairs, what if instead of so what if the strawberries still represent hydrogen? This is a carbon, but I'm going to take one of them off, and instead I'm going to have, this is, the blueberry is going to be, that's going to be chlorine now. All right, so there's a couple of things going on here. I know I'm losing my 3D shape here, but the carbon-hydrogen bonds, electronegativity-wise, are nonpolar bonds. The carbon-chlorine bond, on the other hand, is not only a polar bond, but it's really distinctive from everything else in the molecule. So you can always find where the chlorine is. There's nothing else in this molecule to cancel out that polarity. So it's easy to get oriented to this molecule. You can always find where the chlorine is, just like you can always find where lone pairs are. So yeah, you're like, oh, yeah, I can find that. This molecule has a top. That's what I refer to. It's not literal, it's just figurative. But hopefully that kind of makes a little bit more sense. Now, let's try to talk a little bit about sigma and pi bonds. This has to do, now we didn't cover it a lot in class, so if you really want to get into the spatial orientation, you need to go back and look at chapter 7 when in the book where it gives you the 3D renderings of S and P orbitals. But generally an S orbital looks like a sphere. It's a ball. So an S orbital looks like a ball. And a P orbital looks like a dumbbell. Yes, I have dumbbells. So now, when you have multiple bonds, so not just single bonds, I will tell you, are always sigma bonds. Sigma, the way I remember that, is side by side. So generally you're going to have a hybrid orbital. But even if you don't, so these are going to be spheres. My fists are spheres. The only way that they can connect is side by side. So it's always a side by side, end to end. If you're talking about hybrid orbitals, they're going to be like this, so side by side. Now that's important because when you have sigma bonds, you can rotate them. There's free movement around here. They're end to end here. That's not exactly how I wanted to do that. Okay, so here it's end to end. So they stick together like this. So this one can move, this one can move. There's free rotation. So you can't just twist it a little bit and break it apart. So sigma bonds are always what forms first. They're the side-by-side overlap of either s orbitals or hybrid orbitals, the hybridized orbitals. So the s orbitals, single bonds, sigma type overlap. Pi bonds. Pi bonds only matter when you have double and triple bonds. So you have to kind of get oriented a little bit, and I don't have enough hands, so I'm just going to try this. So you have these molecules, and they're bound like this. Well, if you need another bond, there's not enough room for another one to overlap side by side. So how does that happen? Well, so this bond is already happening. What the other way is it's gonna overlap on top and the bottom, like one on either side. So here, these are your hybrid orbitals. Now remember, p orbitals are shaped like dumbbells. So, let's see if I can do this. They're gonna go around this sigma bond. Oh, I've almost got enough hands, almost. So they're going to go around this sigma bond here and touch. Do you see where the dumbbells are touching? And then you have the sigma bond that's in the middle. Okay, so the sigma bond is end to end, and the pi bond is connected in two places. So right at my nose and then at my knees down here. And then your sigma bond is here in the middle. So this is a double bond. Now, when you're talking about pi bonds, yes, it's connected in two places, but these places of connection are rather tenuous. So when you add them in with the sigma bond, so you have a total of 3 points of contact, so the two pi's and then the sigma, double bonds are stronger than a single bond, but what happens if I twist this molecule? If I twist it, the double bond breaks, but look, my sigma bond is still intact. So there's not free rotation. So pi bonds overlap twice, so they're easier to break. You just have to twist the molecule. Sigma bonds, much harder to break. Now, I don't have enough hands, but if you were to have a triple bond, you would have another set of p orbitals. The sigma ones are going to be in the middle right here. And what would happen is, imagine I'm leaving these dumbbells in the same, so these are still here, so kind of like take a screenshot or something. They're going to have, another set of p orbitals is going to overlap in two places in this direction. So you can only see one point of contact, so they're going to be, you know, like around. So here's your sigma bond, and then I have a point of contact for p orbitals in the front and in the back. So there's, and then you have your other set that goes around like this. So that would be a triple bond. You would have, if I had another set of dumbbells and enough hands, they would all go around. And again, pi bonds, easy to break. So you twist it and they break. Sigma bonds, you can twist them all you want to. They're not going to break apart. Maybe I should go sigma bond. Sigma bond, not going to break. You can twist it all you want to. Free rotation. Now, take home points though. A single bond is always a sigma. Sigma bonds always form first because they're the easiest, because it's easy to touch right here end to end. It's also strong. Pi bonds form next. So they would be these overlapping top and bottom. So 2 points of contact is what that would look like. Then if you had, so this would be a double bond, so one sigma bond, one pi. Then if you had another, a triple bond, the orbitals would overlap like this. So you have your sigma bond right here in the middle, and then your 2 points of contact up and down, and your 2 points of contact forward and back. That's kind of what that looks like. I know it's weird, and I don't have the best models to show it, but that's kind of what that means. So hopefully that makes it a little bit clearer for you. But good luck. Polarity is something that, for me, it didn't make any sense. And then one day I was like, oh my gosh, I get it. So hopefully just play around with it. Get some models out. See if you can figure out what it's talking about. Look up, you know, maybe some other exercises. Maybe somebody else has got a better demo, if that's possible. And I'll just kind of work with what I've got at home. So good luck, and let me know if I can help.